Last lecture I said there wasn't a whole lot of research on these various variance reduction techniques. That's actually can easily be misinterpreted. There's been a tremendous amount of research on using these various techniques for evaluating one integral. That's where the literature has arisen. We're not using it for that purpose. Our purpose, we do evaluate an integral, but what we're really doing is estimating parameters on the basis of sums of nonlinear transformations of integrals. And in that context, these have been studied very, very little. So that's the context in which if you want to do a paper on this, you'd want to do it. How do the estimates change, and what's the variance in the estimates based on different types of variance reduction for the integrals? This takes into account something that's not studied in the standard literature, which is the canceling out across observations when you're taking a sum, and it includes the issue of bias within the nonlinear transformation of the integral each time along. So those things you'd have to deal with, which haven't been dealt with before. Okay, that's done. So what today's topic is an attempt to get closer in for each person on what their actual tastes are. The whole basis of microeconomics is an understanding that different people have different tastes. We spend our money differently because of that, and microeconomics is in a sense the analysis of how all these various tastes go together to create markets and create prices in those markets that then serve all people's tastes. But it starts with the idea that each person has different tastes. What we've done with our mixed logits, and you can do it with probit also, is to estimate a distribution of tastes in the population. So let's say this is willingness to pay for campgrounds. This was an example we used before. And it's centered on a particular mean, which is positive, as we found. The average person likes having campgrounds. There's a considerable number of people that dislike having campgrounds around, and other people that do like having campgrounds around when they're going fishing. Okay? So we've estimated the population distribution, and that's very important. That's usually what you need for forecasting for the population. But sometimes what you'd like actually is to find out where an individual person is within this distribution. If you're looking at one individual angler who's going fishing, is that a person who, for example, tends to dislike campgrounds? What can we say about that person's individual tastes? Now, there has to be some way to do this. In theory, you'd think there has to be, and in fact there is, to look at the tastes of the individual person. Because each person's choices reveal their tastes. That's the basic idea of revealed preferences. If you see a person consistently going to sites that don't have campgrounds, and even when there's sites with campgrounds that are closer and easier to get to and have just as good catch rates, then you can infer from that that the person must not like having campgrounds around. Now, there's a limit to how much we can learn from a person's choices, because usually you don't observe but a few of their choices. You might observe a person buying a car maybe once every 5 years, or taking fishing trips maybe twice a season. So you don't observe a tremendous amount about the person. If you observed a lot of choices by one person, you could just do estimation on that person's data by itself and get a standard estimation for that person. But when you don't have that information, we still can infer some information from the limited amount of choices that are available. Essentially, we know what the population looks like. We know how this person's choices differ from other people in the population, and from that we can infer where in the distribution they're more likely to fall. So what we want to do is formalize those concepts. What kind of information can we obtain? How do we really interpret that information? And how do we do that inference from a population to an individual by looking at that individual's choices? Now, the distinction that I want to make that's the basis for all of this is there's two distributions. You can think of different distributions of the parameters, the taste parameters. The distribution that we've been looking at so far is taste parameters are distributed, I'm calling it G. I'll get another marker. This is the distribution of parameters in the population. So these are the mean and variance, say, or the whatever parameters identify that distribution. This is the mean and the variance in the population. This is the density of beta given that mean. So if it's a normal distribution, you get a mean and a standard deviation or a variance, and that tells you what's going on in the population. This, if you're looking at it in a frequentist terms, means that each person in the population has different tastes, and this describes that distribution of tastes over all people in the population. This conditions only on the information of the parameters of the population distribution. What if you were to look at a group of people, however, all of whom faced the same choices and made the same decisions? So suppose you're looking at a subset of a group of people, all of whom had certain fishing sites available to them and chose a particular fishing site, a given one. You can look at the distribution of beta within that subpopulation. Call that H. That's the distribution of beta within the subpopulation of people who make a particular choice. Okay? So Y is the chosen alternatives, either the chosen alternative in one choice, if that's all you're talking about, or the series of chosen alternatives in a series of choices. Okay? So now we're conditioning that we know the population parameters and we know the choices that this person made. So this is in the subpopulation of people who chose Y. You can even look at it what's the matter with these markers this week? So the idea here is, if you observe the choice of every single person in the population, some of them would make the same choices. Some of them would go to this site, some of them go to this site. All the people who make the same choices, the same outcome of their decisions, look at that subpopulation of people, and there's a distribution of betas within that. They don't all have the same tastes, but all of those tastes led to them making the choices that they did. They all ended up making the same choices. Notice that you don't even have to observe, when you're thinking about this, this is not necessarily people who have already made that choice, but people who would make the choice if they were facing that option, those options. So you can think of it in a conditional sense. What is this? Would? That's not conditional. Subjunctive. Obviously, there's a different subpopulation for every possible set of outcomes. Okay? So you can think of the population as being divided into subpopulations, with each subpopulation being those that made particular choices or would make particular choices. And the aggregate of all the subpopulations gives you the population back. So if you get this distribution H for every value of Y, you can think of this intuitively as the population distribution is the sum over all possible Y's of this. Because essentially you're just breaking the population into different groups. So now what we want to know is, if this is the population distribution, and we observe a person who's making a particular set of choices, then they're within a subpopulation of people who would make the same choices. We want to know what the distribution is for those folks. And actually, there turns out to be a very straightforward way to derive this from that, using the information we've already developed for mixed logits. Yeah?
If you didn't have something like the data where you know, that survey data where you called and asked them, you know, given your choices, what would you do, but you had something more like the BART data, then you couldn't condition just on choices, right? Because they would have had different distances to travel and their values would have been different.
Right. How to think about it. You can still do this. You need to recognize how to think about what you're obtaining. There you get one choice for each person. You observe which mode they chose, given the cost and time associated with each one. And what you're saying is there's no other people in the population that face the same choices in time. So you don't want to take everyone who chose BART because they're not choosing BART under the same conditions. There you are really using this would choose. If you put everyone in the population in the same setting that one person was in, they face the same time and cost for all these modes, and looked at the subgroup of them that chose BART, then we're deriving the distribution of taste for that group. So the idea here is what we're going to be deriving, say you observe an individual person choosing BART. What we're going to derive is the distribution of tastes within the subpopulation of people that if they faced the same costs and time as that person would have also chosen BART. It's a hypothetical concept. Now, that's no different than saying what a probability is. That's important. This is not a stretch beyond anything we've thought about so far. A probability tells you, for that person, if we had a probability of BART, it's telling us if we had everyone facing the same time and cost as this person, what share would take BART? Now we're saying for that share, what is the distribution of tastes? So we're doing the same kind of hypothetical of what people would do if they face those same conditions. That's an extremely important point. That's the biggest confusion in doing this, is what exactly we're estimating.
This thing where you have, looks kind of like the law of total probability.
Huh?
Except it looks, I don't see why there's not some probability weighting over the distribution of y on the right side.
Yeah, this is just intuitively. I'm just trying to get the idea. I'm going to give a complete, a precise relationship between the two. But the idea is you sum up over all the subpopulations, their individual densities, you're going to get the density for the whole population. All right. Okay, so how do we do this? Let's go back and I'm going to do this for mixed logit. But you can just as easily do this for any model that has random coefficients. If you do a probit model with random coefficients or a tobit or anything else you want to do, the same ideas apply. The utility associated with person number n in time period t for alternative I. So you have each person facing a choice in each of several time periods. You can have only one time period, but this allows multiple ones. Is equal to coefficients that are specific to that person times data that describe alternative I in time period t for person n plus error terms that are IID extreme value. So our distribution or assumptions are that these things are IID extreme value. That's what gives us a mixed logit instead of something else. And the distribution of beta is in the population. Okay, so this is the distribution in the population, this is the distribution in the population. So that's the assumptions we've made so far, the notation that we've used. And let's let the outcome be denoted y sub n, which gives the chosen alternative in each of the t time periods. Okay, so this is the chosen sequence of choices by person n. Now, I'm just repeating what we did with mixed logit. We can condition on beta as a thought process. And conditional on beta, the only thing that's random are these IID terms, and so the choices then become logit, and the probability of the series of choices becomes a product of logits. So there's nothing new there. So the probability of y given beta is equal to the product of t equals 1 to capital T of logit formulas E beta x n t y in t. Okay, this gets a little screwy, but this identifies the alternative that's chosen by in the 10th period. Okay, divided by the sum in t j. Now, where we're taking j over all the alternatives. Okay, so all we've got here is, as we already found out, conditioning on the person's tastes, the probability of their sequence of choice is just a product of logit formulas. Now, the unconditional probability is the probability of those choices depending on the population parameters, which is simply, we're integrating out beta using the population density for beta. Okay. This is the choice probability based on what we as the researchers know. We're going to estimate these, and given our estimates, we can calculate the probability for that person's series of choices, recognizing that we don't know their individual beta and we don't know their epsilons. So this is a probability over all the unobserved factors, which uses the fact that we can condition sequentially, condition on those, and then calculate the exact integral for the epsilons. Okay, so this is what we've done already. You've already estimated models of this form. Now the problem issue is, how do we get this distribution? Okay? How do we get, what can we learn by observing the person's choices about the distribution of tastes in which that person falls? Now, this is based on Bayes' theorem. Bayes' theorem relates conditional and marginal distributions. You don't become a Bayesian by using it. It's pervasive. It's an identity. It's just true. Okay? You can think of this. Next lecture, I'm going to talk about how you can think about all this stuff in Bayesian terms, but you don't have to. What does Bayes' theorem tell you? Essentially, it's saying we can take the conditioning in either two ways. We can say this is the probability of beta times the probability of their choices given beta. Okay, so this is marginal over all the possible choices the person could make. And then this is conditional on that beta. So it's a marginal times a conditional. Or we could do exactly the same thing doing the conditioning the opposite direction. Say, what's the probability of their choices times the probability of their betas given their choices. Bayes' theorem just says you can do the joint probability of beta and y can be described as either type of conditioning. Probability of beta times the probability of y given beta, or the probability of y times the probability of beta given y. You could do it either way. So what that tells you is this gives us a way to calculate what h is. Just divide that on the other side. Well, we've got all of these terms. We've got exact formulas for all these things. So all we have to use then, that then gives us an exact formula for h. This is the probability of the person's choices given a value of beta. This is the population density of that beta. This is the probability of the person's choices not conditional on beta, essentially integrating out all of beta. Replacing this denominator now with what we know the definition is. Okay. What do we have here? Our new density is the old density weighted by the likelihood of the person's choices given a particular value of beta. Okay? Notice that this thing in the denominator is just the integral of what's in the numerator. So this essentially just becomes your normalizing constant. It's what forces this density to integrate to 1. So it's a proper, a correct density. It's a meaningful density. So the denominator really doesn't tell you anything. It's just a constant that forces the thing to integrate to 1. So what that tells us is that the intuitive way to think about this is that the probability that the person has a particular beta, given what we observe about their choices, is equal to the probability of that beta in the population times the likelihood of their choices, how likely it is that they made the choices that they made if they had that beta. That makes a lot of sense. Doesn't it? Yes. I hope so. So essentially what you're doing here, if I can draw this, this again is going to be intuitive and not exact because I want to get the ideas across. You got some probability of any particular beta, and then this is beta here. That's the probability of that beta in the population. And then you've got a likelihood of that person's choices given beta. Suppose the higher beta is for that person, the more likely their choices are. Okay, so this is the probability of their observed choices given that beta. Okay? It's the interaction of these two that give you their density. Multiply them, and you get an H that, I don't know if it's going to maximize there, but it's going to be something like that. Okay? And so you get their H, which shifts the population distribution by the probability that the person's choices would be observed by a particular beta, for if they had that beta. So here, for example, this is the most likely, this is the mode of the population density, but it's highly unlikely that the person would make those choices if indeed they had that beta. So we don't give them a very high probability of that beta. But here, it's less likely in the population, but it's more likely to see their choices given that beta. We give them a higher H. So that's essentially what we're doing. And this H, again, is well, let me get into that in a second. Now, I'm going to erase this, because this is the least, you already know all this. There are several things you might want to do. This gives you the whole density, H, but usually you're not interested in the whole density, or you don't want to hold all that information on your computer disk or whatever. You might just be interested in what is the mean of beta in this subpopulation. Here, when you're talking about the entire population, you often talk about what's the mean beta in the population. Now you might be interested in what is the mean beta in the subpopulation of people, all of whom would have made the same choice when facing the same options. Okay, so now the mean beta in the subpopulation of people who would have made the same choices as person N when facing the same options as person N is the integral of beta times this conditional distribution. Okay. Notice that this is very similar to the mean in the population. Forgot to put the d beta there. The mean in the population is the integral over the population density. All we're saying now is let's take the integral over the density within the subpopulation of people who made the same choice as this, or would make the same choice as this person. I'm sorry?
Population G of beta given theta.
Theta. Thank you. There. Okay. This can easily be simulated. We're taking a mean. Whenever we simulate, you're always, like I said before, taking the mean of something over a density. And here we're taking a mean over this density. Just plugging in the values. We got all that over. So how would you simulate that? You can easily simulate it taking draws from the population density. We already know we can do that because you had to do that to get your estimates of theta when you're doing your model for the whole population density. So you take draws from G and calculate this. Take the weighted average of those. So it's the sum over draws of a particular draw of beta weighted by the probability that the person made that choice, okay, made the choices that they did, given that draw of beta, and then normalizing it by okay. So we're taking the mean of this thing here over that density, which we can easily simulate by taking a draw from G. For that draw, multiply it times the probability that the person would have made the choices we know they made if they had that beta. Okay? And then to make sure that the thing is a proper simulator of an actual density, you divide by the sum of those probabilities. Okay?
Is the upper summation for the overall ratio, or is it just only for numerator?
This is a simulator of that, and this is a simulator of that.
But isn't the integral the whole thing?
Oh, this integral is constant, so it comes out of this integral.
Oh, okay.
It doesn't depend on beta. That's what makes it easy. Right. The thing in the denominator is just, you're normalizing constant. But it does create bias in this overall simulation because you're simulating the constant and then put it in the denominator. So again, you've got all the stuff we talked about when you have bias in your simulations. You've got to incorporate that here. So n needs to rise, r needs to rise or be pretty high for this to be accurate. So we now get a new mean beta that's specific to that person. Now what is this exactly? Is it an estimate for that person? There's two ways to think about it. The way I like thinking about it is that it's not an estimate. Okay? That it is an implication of your estimates of the population parameters along with what you observe the person's choice to be. There's a one-to-one relationship for the population parameters and the person's choices there is a distribution conditional on those two things. Conditional on those two things, and that has a mean. After you've got theta, there is no sampling variance or anything associated with this mean. It's an exact one-to-one relationship. Okay? It just tells you, if you apply Bayes' theorem to condition not just on the thetas, but on the person's choices, what the distribution would be and what the mean of that is. So again, looking at it that way, you see it in the same, how to put this? See this as, after you've estimated the population distribution, you can divide that density, the population, into subpopulations, each of which has a density, based on the choices that, the outcomes that people would choose under given situations. That is a natural, and it's just an implication of the population distribution and the person's choices. It's not an estimate. It's not a separate estimate. In fact, in that sense, it doesn't make sense to have a separate estimate of the beta for each subpopulation and the mean for the entire population. So in that sense, you don't think of it as an estimate. And in fact, that's nice because you don't have to think in terms of asymptotics. You could have only one choice situation observed for each person, and this just tells you, in this subset of people that would make that choice given the same situation, what the distribution is and what the mean is. Now, what that leads to is, as you get more and more observed choices for a person, then this y becomes longer, and you would expect there'd be fewer and fewer people who would end up making exactly the same series of choices that that person did. You know, if there's one choice being made, like which mode to take, if you have the whole population facing the same time and cost as that person, quite a few would end up taking BART. But if you have the person observed over, 15 years worth of choices, it's highly unlikely you'd have very many people making the same sequence of choices as they do. So what that means is that as y gets longer, this, in the way I've been thinking about it, the subpopulation, say that's the population, the subpopulation gets more and more centered on that one person, because there's fewer and fewer people that are like that person. But for any particular y, you're still estimating the distribution in that subpopulation. It's just that as y expands, your subpopulation shrinks, and you're getting fewer and fewer people, and so you're centering more on exactly what that one person does. Okay, but in that case, for a given y, you're still estimating just for that subpopulation. Now, what this, though, does is allow you to think about this as an estimate also. You can think of this mean of the conditional distribution as being an estimator, which, as the number of choice situations that the person faces rises, is consistent in the sense that it converges on that person's exact betas. Okay. So the first way to think about it is that it's not an estimator, it's a natural implication of your population distribution and the person's observed choices. And there you don't have to think about the number of choice situations rising. There's no reason to think of asymptotics. You're just saying, for the choices we observe, however many that is, there's a subpopulation, and that's what the mean is. Or you can think about it as an estimator under the concept that the number of choice situations for that person rises without bound, in which case the mean of this distribution becomes a consistent estimator that converges in probability on that person's true beta. That second one's a little strange because it's rare that you actually observe. You can get a sample size that's bigger and bigger and bigger by just choosing more and more people. It's hard to get number of choices for one person rising without bound. And in many situations, it's just logically impossible. College choice. I mean, you don't go to college, 500 different colleges. Most people don't. So, there's a natural limit. But you can think about it either way. Yeah?
What's the benefit of doing that as opposed to just estimating a different parameter with a different distribution for people of different types, for people who choose this versus that?
Like the exercise we did in the very beginning, you had different scales for different subgroups.
If you could identify people, how to put this? If you don't, in the BART situation, you might observe a lot of people choosing BART, but they would be choosing it under different costs and times. And what you don't observe, what they would choose if they all face the same cost and time as this one person. So you don't observe the data you want to observe to do what you're describing usually. If you did, then you could divide it into all these individual groups, but then you wouldn't have any variation in the dependent variable. So you couldn't do estimation. Except over time, if you had a lot of time periods, in which case that becomes equivalent to estimating for each individual person over their individual observations if you had enough time periods for each person. It's a good question. Stumped me for a while. Okay, so this is, you can get your mean of the conditional distribution. And as we'll see, this can be very useful for characterizing marketing opportunities. You can say, okay, well, we know this person's not just, has this as their mean for the, they're not just typical of the population. They're from a subgroup that has a different mean. Maybe we can find a product that actually works well for them and sell it to them. I'll show you that with an example later. But the other thing you can do is to get better predictions of the probability in a new choice situation. Suppose now we have observed the choices of people, estimated our model, and we want to predict what they're going to do in a new choice situation. So we've built an extension to BART or something and see how that affects people. So let's say this is time period t plus 1, and we want the probability of alternative I, that they'll choose alternative I in period t plus 1. The probability of alternative I for person n in t plus 1, given the population parameters, is simply our logit model, E beta x n t plus 1 I. So we essentially just calculate the mixed logit J, integrate over the population distribution, get that. So this would be our probability for the person, conditioning only on what we know about the population distribution. And if you're doing market forecasting, that's probably fine. You don't really care which individual person's doing what. All you care about is what they're doing for the population as a whole. But what if we wanted to look at one individual person? We could get a better estimate of what they're going to do in the next period by conditioning not only on the population density, but on their previous choices. Okay? So this is the choices up to period t. And so we're conditioning on that. We're going to say, well, we're going to take the information. We already know this person's chosen, transit over and over again or whatever. Now we're going to use that information to get a better estimate of prediction of what they're going to do in the next period. That's the integral of this logit formula. Okay, over their conditional distribution. Okay. So instead of conditioning on the population distribution, which says we don't know where they are, we're going to condition on their conditional distribution, which is the distribution of tastes within the subpopulation of people who make the same choices as this one. This gives us a better prediction for that person. Essentially, we're saying we're going to use the information on their previous choices to get individual level predictions for what they're going to do next.
So that assumes that there is some state dependence. So why couldn't you put the state dependence in the original model in the first place and have used information about if you have a panel?
This is different from state dependence. State dependence, first of all, you can do what you're describing, and I'll get to that in a second. But the way I've been describing it, this is different from state dependence. State dependence tells you that when a person's made a certain choice, they're making that choice their experience of that alternative affects their future evaluation of things. Here what we're saying is their previous tastes are revealed through their choices, and we're going to use that revelation to do a better prediction.
So you're trying to capture the heterogeneity.
Right. Now you could put state dependence in this also, and it just layers on top of everything. It doesn't affect anything. We need to stop? Okay. Okay? Great. So, question.
You keep saying that it's the people who would have chosen Y in the same situation, but I mean, maybe I live far from BART, and I would have chosen BART if I had lived closer because I like public transportation. But I don't see how you're getting that would have chosen front since you're conditioning on what they did choose.
Oh, I see what you're saying. The way to think about this, the notation is a little bit inadequate, but if you get correct notation, it just gets so cumbersome it's not worth it. You should condition on Y in conditioned on X in, which is the attributes that nth person faced. So think about BART. Suppose from my house I have particular time and cost of going to BART and the bus and driving and everything, and I make a particular choice. What we're now trying to find out is, given that I made that choice, what is the distribution of tastes in the subpopulation of people that if all of you, everyone in the population, were put into my house and had to make the choice, would end up making the same choice I did. So my choice is observed, but the rest of the population's choice, who constitutes the subpopulation, is not observed. But we know that if we did that experiment, Bayes' theorem tells us that this would be the distribution of tastes within that subpopulation. So that's the experiment that you're thinking of. If we forced everyone in the population to make the same choice, to face the same choice situation I faced, what would be the distribution of tastes in the subpopulation of people who end up making the same, choosing BART like I did? So we're conditioning on the choice that one person made, he or she was observed to make, okay, and then deriving what is the density of betas in the subpopulation of people who would have made the same choice if they were forced to make that choice. That's why I say would have down here, or would choose. There's another question here. Again, this is on the same footing as probabilities. The probability that I would choose BART is if everyone in the population were forced to live in my house, what share of them would take BART? And that's, so we're doing the same kind of thing here. Okay, so we can simulate this very easily. You simulate this by taking draws. Just know that H is equal to this thing here. So take draws from G, multiply the probability of the person's previous choices, given that value of B, times this thing evaluated at that, divided by okay. So we, again, take draws from the population distribution, which we've estimated, multiply it times the probability that that person's choices, of that person's choices given that value of beta, and then multiply that times the probability for the new choice situation. Essentially, this is the average of these logit formulas over all the different betas, with the betas weighted by the probability that the person would have made the choices that they actually are observed to have made in the past, given that beta. So it's using this information to simulate this probability, which is not conditioning on their choices. We take a draw from G and calculate the logit model, logit formula for the new choice, okay? And we do that for every possible value of G. Here, all we're doing is the exact same thing, but instead of just calculating the logit, we're multiplying that logit or weighting it by the probability that they would have been observed to make the choices they are observed to have made in the past. That tells us how likely that beta is for that particular person. Okay? And you get better predictions here. You're conditioning on more information. Yeah?
I have a question, so sort of going back to this other one. Hope I can get it out in a
Okay.
confused manner, but This was looking at, say you made a choice for Bart, and the question is, how would the rest of the population or group, had they been in that similar situation, chosen? Suppose you and somebody else chose Bart, but you're in a somewhat different situation, but you made the same choice. Are you and that other person in the same subgroup?
No.
Okay.
Those are two different subgroups and would end up with different H's because the explanatory variables, the time and cost, will determine how much information is revealed about that choice.
So it's not that we're trying to identify people with the same taste. It's rather given people with the same situation, what is the distribution of taste for them?
Right. One extra phrase needs to be, given a group of people who face the same situations,
what is their distribution of?
What's the distribution of taste within the subgroup that would have made a particular choice?
That could have.
Yeah.
And their situations are sort of defined by the X.
Right. Your situation is defined by X, and then if everyone faced those X's, some of them would choose a particular Y. And it's that. It's hard to think in these terms. But actually, when you start thinking about it, it starts having this incredible power. I mean, it's really on the same footing as a probability. It's just harder to get to that way of thinking. It's, again, you're doing a hypothetical here. Okay, so let's break for 12 minutes till 10 after, and I'm going to show you an application and show you the incredible power that this gives you. Using these procedures, I have two kind of numerical examples to show you. One is a Monte Carlo study where the data are made up. The advantage of this is that we know the true tastes of each person in our made-up data set. So unlike when you have real-world data, you can see how well your estimates are doing compared to what's truth. So I want to do that first, and then show how this is used in a real-world data set. So first of all, we did a model, I did a Monte Carlo study where there were 3 choices that the person faced and 4 variables. 2 of the variables were fixed and 2 of them varied in the population. They varied with a mean of 1 and a standard deviation or variance of 1, just so we can compare things. Now this is one respondent, the first respondent. And we increased the number of choices that person faced. This is the population density. It's centered on 1 for each of the 2 varying parameters and has a variance of 1. Okay? So if you didn't condition at all, this would be what you'd think the distribution of parameters were. But for this one person, if we observed 1 choice, you can see it kind of moves over and gets a little bit steeper with just 1 choice. If we observe 5 choices for the person, then it goes further, and by the time you've got 10 choices, it's pretty steep. You've got a pretty good idea of where that person's actual tastes lie. Notice that this is 10 choices in a 3 alternative thing with 2 random parameters, so it might be overemphasizing how much information you get from each choice. But you get the picture here is as you get more and more information about what that person's choosing, that reveals more about their individual choices, and so the conditional distribution moves over. Notice also what I said before, that if you think of this as not an estimate, but just an implication of Bayes' theorem combined with the population distribution, this is the subpopulation of people who made the same choice as this person in that 1 choice situation. Okay? Here, it's the subpopulation who made 5 choices, all of which were the same as this person when facing the same explanatory variables. So you'd expect this subpopulation to be smaller than that subpopulation. The density, of course, is normalized to integrate to 1, so the density has the same mass. But there's fewer people here, and even fewer here. So that's why it's kind of getting more and more, the subpopulation that it's referring to is getting smaller and more homogeneous. That's what's going on here. And here gives information on how the means of the conditional distributions relate to what you'd have if you had perfect knowledge or if you had no knowledge at all about that person. So let's just, we don't care about the number of Halton draws, just look at this one, most Halton draws, so it's the most accurate. In each of these, with this many choice situations, I calculate the standard deviation of the means of the conditional distribution. So for each person, we calculate the conditional distribution that's relevant for that person and the mean of that. So for each person, we get a mean of their conditional distribution. And we calculate the standard deviation over people. Okay? This standard deviation, with no conditioning, what would it be? 0. If you don't condition, everyone's going to get exactly the same mean beta because they're all going to be given the population distribution. If you just say, okay, well, we don't know anything about this person's choice, then you just give them the population distribution. Everyone has the same mean. If you have full knowledge of beta for each person, then the standard deviation of the expected betas for each person are going to be equal to their true betas. The expected betas for each person are going to equal the true betas if you had full knowledge, like an infinite number of observed choices for each person. And the standard deviation then would be the same as the standard deviation of the betas in the population, which in our Monte Carlo is 1. So what we have here is the standard deviation ranges from 0 to 1. 0 means no conditioning at all. You don't learn anything about the people from their choices. To 1 where you have complete information about their individual choices. With one choice situation, this has risen from 0 to 0.4. By observing only one choice situation for these folks, you've gone 40% of the way towards full knowledge. That's quite a hefty increase. If you observe 10 choice situations, you've gone 82%. And you know, there's highly decreasing returns as you get more and more choice situations. But it gets closer and closer to 1 at a decreasing rate. The absolute difference, this is just standard deviation. You can calculate that for your population with real world data because it doesn't take into account what their true is. You know what their true is, and our example is 1, so it moves towards that. Absolute difference, this is the difference of the mean of the conditional distribution for each person minus what we know their true beta to be. Okay? So this is how much error we've got in using that mean as an indication of that person's actual estimate. And this is the absolute difference. It starts at 0.8. You can calculate this, but if you've got a normal distribution with variance of 1, the average absolute difference is 0.8. You can just go calculate it. And it goes to 0 when you have perfect knowledge, such that the expected beta, the mean of the conditional distribution for each person, is exactly equal to their true value. So here, it's getting smaller as you get more information, starting at 0.8. So with one choice situation, it went from 0.8 to about 0.72 for each of the 2 random parameters, which is about a 10% movement down towards perfection. Here you get at about half, goes from 0.8 to about 0.4244, something like that. And again, it gets lower and lower, decreasing returns. So both of those are telling us the same thing. First of all, we get quite a bit of information with just one choice situation. And you get decreasing returns. As you get more and more choice situations, you get a better estimate or a better concept for each person, but you're decreasing returns. There's one other thing that's important to notice here, though, and it comes up in real-world situations and evaluating this. Notice that if you look at the standard deviation, we've got a 40% improvement from what would happen with no conditioning. So it looks like we've got 40% of our way towards perfection. Okay? Whereas if you look at the absolute difference, we only got a 10% improvement over what we'd have with no conditioning. What that tells us is that standard deviation of your conditional means is going to overestimate the amount of information you have. Why? Some of these people's conditional means are actually moving away from their true. Just when you observe one choice situation, use this conditioning, it could be that the conditional mean for this person is actually further from their true than it is for the population as a whole. For example, suppose this is the population density. This is the conditional density. This is the mean in the population. This is the subpopulation mean. But suppose the person's out here. The person's, we don't know, I mean, the person can be anywhere in this conditional distribution. And in this case, the population mean is closer to the person's actual betas than the subpopulation mean. Eventually, as you get more and more choices, this is going to move back and center on this. But when you have a finite number of choices, it could go further away. So the standard deviation in your expected betas incorporates movement away from the true value as well as movement toward the true value. Okay? And so it, in a sense, overemphasizes how much information you've got. You need to remember that when you're doing your stuff. Okay, so now I estimated 4 different models. Oops, sorry. We don't need to go over these in detail, but I can't remember if this was the mixed logit exercise that you did, where you estimate this is choice of supplier. You've got price, fixed price, length of the contract. Yeah. So you've estimated these models, these kinds of models. I did ones with all normal distributions, all uniform distributions, all triangular distributions, and then one in which the price, all of these have price fixed, in which the dummies for time of use rates and seasonal rates are log normal, because you have to dislike paying money. They're like a price kind of thing. And these are normal. So I included some log normals to account for that. This is the best fit, where you have the log normals that keep price coefficients of the right sign. It's comforting to realize that when you impose rationality, that it actually improves your model. And from each of these, you can calculate, these are the population parameters. You can calculate the willingness to pay for contract length, whether it's a local supplier, all that kind of stuff. And you've already done that in your exercise. Now, so this gives you the population distribution. What I then did was to calculate for each individual person what the conditional mean for that person was, given their observed choices, and the conditional distribution and the mean of that conditional distribution. Now, I think the best illustration of how valuable this is comes from this table right here. These are the population betas, averages, mean betas. So if you knew nothing about a person and you were just getting your best guess for that person, what their betas would be, you'd give them this. But now suppose you condition on what their actual choices are. For each of these are the first 3 people in our data set. I didn't look for them for any particular reason. I just chose the first 3 and calculated the conditional distribution for them and the mean of that. And this is the mean of their conditional distributions. You get incredible information that is great from a marketing perspective. If you are actually trying to find out what to do with your customers, this is very useful. The population in general dislikes contracts, but this person really likes contracts, a considerable amount. He likes the local utility, but not that much more than just in general. And the known company likes known companies, but not that much more. But notice, the main thing is, unlike the population in general, the average person in the population, this person likes long-term contracts, and these coefficients are extremely small for time of use rates and seasonal rates, extremely non-negative. Essentially, he thinks that these 2 rates are less bothersome than they actually are. This translates into equivalent fixed price of about 6 cents for each of these, 6 cents per kilowatt hour. This person is being irrational. Notice that the rates under here, seasonal rates, the lowest it can get is 6 cents. For time of use rates, the lowest it gets is 5 cents, and so they'd get an average price of 6 cents only if they use practically all their consumption off peak. Okay? So this person thinks these two rates are equivalent to 6 cents, which is at the very low end of the distribution. For seasonal rates, it would be impossible to get 6 cents. That would mean they're not consuming anything in the summer. Time of use rates, it's possible to get 6 cents as an average price, but that would mean very, very little on-peak consumption. It's possible, they're just not home then. For seasonal rates, it's not. So what you've got here is a person who really likes these variable rates and thinks they can take advantage of them and values them at about 6 cents, which is very low. Either they're right or they're diluted. For the seasonal rates, they have to be diluted. It's impossible to get that low of an average price. And they want a long-term contract. Well, what would any rational profit-making utility do here? Go out and offer them seasonal rates at a price that is going to lose them money and make you money, 6 cents a kilo. Am I getting this right? Yeah, you offer them these seasonal rates, which actually cost the person more than 6 cents per kilowatt hour, but they evaluate them as if it was 6 cents. And so they are willing to accept them even when it ends up costing them more. And you lock them into a long-term contract. So by the time they figure out they're wrong, it's too late. They're already locked in. And they voluntarily go into this. So here's a person, if you're doing this on your computer at PG&E, you just call up this person and say, hey, we got these seasonal rates. You'll love them. They're 10 cents in the summer, 6 cents in spring and fall, and this person will say, oh, I like that. And not only that, but we'll sign you up for 5 years. So you won't have to worry about, Now, the ethics of this is a separate issue. What this is telling you is that you get a tremendous amount of information that has specific marketing implications. This is like taking price discrimination, product discrimination, to a new level. It's like, this is like perfect price discrimination stuff. These aren't their, this is just your estimate of their actual, or this is not their actual true taste, but you're getting some information and able to price discriminate. This guy, let's go back to. This one, customer number 3, they dislike long-term contracts more than the average person does. They don't really seem to favor the local utility that much compared to most people favor them a tremendous amount. About 2.5 cents per kilowatt hour is the willingness to pay for the local utility. This person's not willing to pay for the local utility like that, but they really dislike these variable rates. Okay? What this looks like is a marketing opportunity for some new provider. The new provider has a better chance of capturing this customer than others because they don't have such a bias. The customer doesn't have such a bias in favor of staying with the local utility as much. So they're easier to capture. And you capture them by just saying, I'm going to give you fixed rates. Don't have to do anything. You don't have to sign up, don't have to have a contract, just agree to change to me. So you don't have to sign into a long-term contract. You don't have variable rates or anything. Just come to me. I'll offer you a little bit lower price. And you don't have to offer as much of a lower price to get this customer compared to an average customer. So if you're a new firm coming in providing electricity, you're going to want to go through and not market to everybody. It's going to be a waste of time. You want to find people like this that don't have much of a emphasis towards the bias towards the local utility and offer them something that'll work. And here's one of them. Customer number 2, I don't see anything about that customer that is particularly remarkable or that could be used for marketing. So actually I like that. It kind of completes the picture. You don't always get valuable information. You sometimes do. And it can be, very specific valuable information. The local utility should go in with a long-term contract for variable rates. Here, some other new supplier should come in, no contract, fixed rates, just a little bit lower price. Do you see anything going on with this person? Nothing really remarkable. If anything, you can get them for time of use rates, but that's not that much lower to make it worthwhile. Now, this kind of customer-specific information where you get a conditional distribution for each person and look at the mean or maybe the whole of the conditional distribution has taken off in marketing circles. It's really the hot item right now. And so and it's because of exactly what I've described. It really takes this marketing concept to a new level. It allows the firms to figure out who they should approach for target marketing of products. And it's useful. However, I want to point out some limitations before, kind of mitigate against this, this overemphasis on this. This is only useful for customers for whom you've observed their previous choices. They don't have to be in your estimation sample. It could be that you estimate your model on one sample and then go out and find choices for other people. Like you call up a person and ask them, well, what have you been choosing for the last 5 years or whatever? And you get their information, feed it into the computer while you're sitting there at the telephone with them, and it spits back your answers. I mean, it happens in seconds, this conditioning. And you get your answers. But if you don't know what their previous choices are, you can't do this conditioning. This is a big limitation. This is not useful for mass programs or mass advertising. It's only useful if you can observe somehow previous choices of individual customers and then do marketing on an individual level. So in terms of our sample, we can do this for everyone in our sample, but then when we try to generalize to the population, we're back to just using the population stuff. You're not able to generalize because you don't know. I mean, you assume the past choices of your sample is like the population, but still it's just described by the population density. This is only useful if you can get for individual people their past choices. Yeah?
I don't understand why you need past choices. Why can't you call a large sample of individuals and ask them what choice they would sort of consider evaluate?
You could. And in fact, I want to do that. I'm trying to get a couple firms to fund it in real world situations. You could ask them these kind of choice experiments on the phone. But it still means, I guess all I'm saying is you have to do that on an individual basis. If you're predicting for the population, you get exactly the same predictions if you use the population distribution for everyone as if you use the individual level conditional predictions for each person and then add up to the population. So it's only useful when you're going after individual people. Now, what I would really like to do is find someone that has a tremendous number of products, and you set up a set of experiments where you ask the customer, okay, here, if we offered you these services, which one would you like? Okay, well, now that we know that, here's another set that you might even like better. And which one do you like of that? And so you get that information from them while you're sitting there in real time on the phone with them. The machine can calculate, and then it can figure out the product to offer them at a price that they will consider to be good and that will make you money. So it's essentially a formalization of perfect price discrimination. And then how much is shared with the customer versus kept by the firm is, depends on how far you can push that concept. But notice, this sounds draconian, but you actually end up with the customer being better off, because you're finding something that meets their taste. Okay. Now, those were for 3 customers. I did it for all the customers, found out what the mean of their conditional distributions were for each of the models. Some things that are interesting here. First of all, the means of the conditional distributions are practically exactly the same as the population means that you get from the previous table. That's to be expected. It's what I said. If you take the subpopulation, all the subpopulations, their conditional distributions, add them up, you get the population density. So the mean over the population is the same as the mean over subpopulations of their individual means. And that's what this gives you. Okay. The standard deviations of these conditional means is less than the standard deviation in the population. Okay. That's because this method only gives you partial information about each person. A person's actual taste can be this far, but because you don't observe an infinite number of choices by that person, you can't observe that exactly. So what this does is, if you have no information, it's at the population mean, and you move towards this person's true betas as you get more and more information about them. So the standard deviation of these conditional means is going to be lower than the standard deviation of the true betas in the population. Now you can get a sense of how much information you're gathering by comparing this. This is 0.32 is the standard deviation of these conditional means. If you go back to table 2 where the model is, the estimated standard deviation is 0.38. So we've got about 80% of the variation in betas captured through this conditioning. Okay? That's pretty good. That's true with all of them. The other thing that's interesting here, I didn't describe this, but it's in the paper. You can calculate these conditional means at the point estimates that you've got for your population parameters, but you can also take the variance in your population estimators into account and how to put this. When you estimate the population parameters, you get an estimate and standard errors. That essentially saying that you've got a normal distribution with that mean and standard error for your estimator. You can take draws from that distribution, and for each draw, calculate the conditional means. Okay? And that gives you a distribution of conditional means that incorporates the sampling distribution, sampling error that's in the estimates of your population parameters. So you can carry that on through. The details of that are not that relevant. But here is when you ignore the sampling distribution in your population estimator, here's where you incorporate it. What's interesting here is that these three models, the mean of the conditional distributions does not equal your estimated population mean for these three models. That, in a sense, is a specification test. As we've said before, you take the subpopulation distributions, add them up, you should get the population distribution. So the mean of the means should be equal to the population mean. And if it's not, that shows that your model is somehow misspecified. And interestingly, the model 4 does not have that problem. So once again, in a sense, I think what's going on here is that in these models where you allow negative, the wrong sign for your price coefficients, you get models that are misspecified, and it can actually show up in this way. When you force the price coefficients to have the right sign, the correct sign, then your conditional distributions are consistent with your population distribution. So this is kind of an example of how misspecification does show up in this way, in addition to all the other ways that it might show up. If you calculate the conditional distribution for each person and add those conditional distributions up, and that doesn't equal your estimated population distribution, then you know something's the matter. Any issue here? Okay, and then finally, we estimated this model on where is this? Here it is. On 11 out of the 12 choices that the person faced. And so we saved that 12th choice situation to use in prediction. So we pretended like we didn't know what they did in that 12th choice situation, predicted what they did, and then compared it with their actual choice.
The sequential one? The sequential one?
Yeah, we asked, in this we had the people,
The last choice.
it was the very last one. So we used the first 11 and pretended we didn't see the last one, and estimated the models, and then used that to predict what happened in the last. So in the last choice situation, we observe what their actual choice was, and what this gives us is what is the probability of that choice using each of the models. If you use a mixed logit without any conditioning, you get a probability of 35. So it's the chosen alternative on average had a 35% chance of being chosen. When you calculate for the conditional distribution using the information that's embodied in the person's first 11 choices to predict their 12th, the prediction goes up to around over 0.5. This is enormous. Notice that with no model, this is a 4 alternative model, 4 alternative choices. So with no model, you get 0.25. That's just chance. With the unconditional mixed logit, it goes to 0.35. So you've got a 10% rise here. And then if you condition, it goes to more than 50. So the increase from conditioning is actually greater than the increase that occurs because of your modeling the population. I was shocked that it actually had that big of an impact. So what this tells you again is conditioning on the person's past choices, if you can get that information, allows you to get tremendously better forecasts of what the person's going to do next. And in a sense, you know, it sounds reasonable. I mean, that's the whole basis of microeconomics, is that, you know, people's choices tell you something about their tastes. And here we're incorporating that explicitly. Now, I calculated this probability in 2 different ways. I said, let's calculate it correctly the way I described earlier. That's what this one is. But then let's calculate it instead by just calculating the logit formula at the expected betas, the mean of their conditional distribution. So I'm using that mean as kind of like, it's not an estimate, but I'm using it as if it were an estimate of their true parameters and putting that into the model. This is easier because you only have to save that one set of betas for each person, and then you just plug it into your logit formulas. That gives higher probabilities, and the reason it does is because it's ignoring the fact, it makes you think you have more information than you do. High probability means you're sure of the choice. Well, what's happening here is that you think you're sure because you think you're treating these conditional means as being indicative of what their true parameters are. So it makes you think you can predict better than you actually can. But notice that it's not that much different. And so if you need to save space or just want to, it's probably not going to be that bad to save information on the mean of their conditional distributions, rather than what's needed here is the entire conditional distribution. Okay. But the main thing is whatever method you use, you get a tremendous increase in predictive ability. Out of the 361 customers, 260 of them, your prediction of their chosen alternative gets better with the conditioning. For the other 101, it gets worse. This is important to recognize. There are people for which this conditioning, it makes you worse in predicting their final choice. There's a variety of reasons for this. One is that, you know, it's just they happen to be on the part of the distribution where the conditioning pushes the mean away for the number of choice situations you've got. Also, it could be that this new choice situation represents a new kind of trade-off that they haven't yet faced. So previous information doesn't really help you much. Their previous choices reveal some of their tastes, but not the ones that are relevant for this new choice. In which case, the previous stuff just adds noise. And you're going to be on sometimes, off sometimes. So you've got to realize you're going to be worse for some people. But you improve for about twice as many people, more than twice, then you get worse off. And the rise in the probability for those that you're improving for is greater than the drop in probability for those that you're worse for. So you get a double whammy in your favor. You're predicting better for a lot more than you're predicting worse. And those that you're predicting better for, you get a lot better prediction than the loss in predictive power for those you're getting worse on. So all this goes to tell you that if you're really wanting to look at individual customers and see, you know, what action should be taken and what that person's going to do, conditioning on their previous choices, even when you don't have enough choices to get an estimate for them individually, but estimate for the population as a whole and then condition to get information about that individual person, it can improve the power of your analysis tremendously. Now, next lecture, we're going to talk about how you can do all of this stuff in and Bayesian procedures too, using other kinds of techniques, which you could generalize to other models as well. Okay, any issues, questions? Good. See you next week. No problem sets.
Also, 2 weeks from now, after their phase.
Next problem set, you start next week and turn in the week after that. Yeah.